Hi everyone, this is Linear Algebra for Business Analytics, and in this video we're going to look at linear combinations, span, linear independence, and the notion of basis vectors. So let's jump right into it. So linear combination is nothing but a way to combine vectors. So last time we saw that we can add and scale vectors, right? So let's say if we have a vector u and a vector v, then a linear combination would be a vector w, which is, let's say, uh, 10 times u plus 2 times v. Okay. So this is called a linear combination, and there's some other notion. I guess in terms of analogy, there's some other notion called convex combination. Um, So it just means that when you get the numbers, for example, if w is equal to 1/2 times u plus 1/2 times v, then this is called a convex combination because the scaling factors sum to 1, and they need to be positive. So it's 1/2 plus 1/2, which is 1. So this is called a convex combination. A linear combination, these scaling coefficients. I'm calling them scaling coefficients, but these numbers in front of the vectors, they need not sum to 1, and they need not be positive, right? So that's a linear combination. So if you think of a generic vector, let's say in 2 dimensions, if you think of a vector u, let's say it's 2, 3, then actually this vector can be written as a um, linear combination of two vectors, which are as follows. So 2 times 1 and 0 plus 3 times 0 and 1. Okay. So I guess back substituted things. So I was given this vector, but I just said that this is nothing but a linear combination of these two vectors. And these two vectors are actually called basis vectors, and I'll explain in a moment why they're called basis vectors. So whenever somebody writes on a vector, right, a point in a space, it's always with respect to what are called basis vectors. For example, when I say there's a point 2, 3, then it's 2 units to the right on the x-axis, and it's 3 units to the north in the y-axis. But it's with respect to the basis vector, which are 1, 0 and 0, 1. Okay. So you can't just specify a point or a vector without, when you specify a point or a vector, you are actually specifying an implicit basis. And that's generally the basis that we call the standard basis. Okay. So that's the notion of linear combination. And just furthering this thought, what if I could change these coefficients to any arbitrary numbers, right? So that's what I said. A linear combination is nothing but a combination of let's say two vectors, and I can put any numbers in the front. So a natural question comes up, which is that what all vectors can I get if I arbitrarily change these numbers in the front to anything, right? And it's easy to see that, in fact, if I keep changing these numbers, instead of 2 and 3, let's say I take 1.5 and -2, then instead of a point over here, I get a point which is 1.5 units to the right and 2 units to the south. So it's something like this, right? Somewhere over here. Right. So and you can see that by changing these coefficients, the scalar multiples, I can get any vector or any point on the 2D plane, right? So so the collection of all vectors that I can get by linearly combining any two vectors, let's say in this case, let's say u and v, is called the span of u and v. So span is nothing but all the vectors that I can create by starting from a couple of vectors. And it need not be just a couple of vectors. If I had 10 vectors, then all the vectors that I can create by linearly combining these 10 vectors. So you can just imagine adding 10 of these vectors with arbitrary coefficients in front of them. Okay, so why is span interesting? So here is a interesting thought. So what is the span of what is the span of vectors 1, 0 and 0, 1? Okay, this we just said it is a 2D plane or the 2D space, right? Now, what is the span of 1, 0, 0, 1, and 1, 1? It is still a 2D plane, right? I mean, you'll see that even if I had one additional vector, I mean, it was not needed actually. I could have reached all the points or vectors in the 2D plane by just using any two of these three vectors, right? So that's interesting. And also, let's look at this. So what is the span of let's say something like 1, 0, 0, 0, 0, 1, and 0, 1, 0. Okay, the span of this is the three-dimensional plane. Sorry, 3 dimensions, 3D space. Okay, and what if I had just two vectors? Let's say 3, 2, 1, and in fact, let me just use 6, 4, and 2. Okay, what is the span of this? Span of these two vectors. Okay, turns out the span of these two vectors is just the line in 3 dimensions. Okay, it's just a line. So you can imagine that, because as you can see that the second vector is actually just 2 times the first vector. So even if I linearly combine them, it's as good as saying I have a single vector, let's say it's 3, 2, 1, and I'm just scaling it all over the place by multiplying it with any number, let's say a positive number 10 or a negative number -5 or whatever, right? So it'll just give me a line in the 3 dimensions. So something which is a line. So if I had two different vectors, let's say 3, 2, 1, and 4, 0, 3, then these two vectors seem different enough that you can imagine that if I come up with all linear combinations of these two vectors in 3 dimensions, I will get what is called a plane in 3D, like a flat surface, like a sheet of paper in 3D. Okay, and a generalization of this, in the sense that if I have let's say 10 vectors in 100 dimensions, I will get a hyperplane. Okay, so what is it's just a generalization into higher dimensions of this notion. And the reason why I brought up hyperplane is because it's related to for example, what are called support vector machines. Support vector machines in machine learning. So support vector machines intrinsically, are a way to classify data into positive or negative classes. And then you can imagine, so the way you would just visually think about this is that there's a bunch of points, as in vectors, which represent our data, observations that I mentioned, or feature vectors. There's a bunch of points, and you want to create hyperplane between them, which somehow separates them. Okay, in the sense, some bunch of points, for example, the zeros fall on one side of the hyperplane and pluses fall on the other side of the hyperplane. So the hyperplane is nothing but a span of a bunch of vectors, which doesn't span the whole ambient space. In this case, for example, there were two vectors, two three-dimensional vectors. They didn't span the whole three-dimensional space, right? Here. Okay, so that's span. Now, so as you saw in this example, the second vector was actually in the span of the first vector itself. So what is the span of just a single vector, v? Okay, so let's think of that in 2 dimensions. Let's say the vector is 1, comma 1, okay, something like this. Then the span of that vector is nothing but all the other vectors that I can get by just multiplying that vector by a number, either positive or negative. So I can get all the points on this line, right? Now, if the second vector, in this case, this is not in 2D, but let's say there was another vector 2, comma 2, or 2 cross 2, or let's say there was another vector 1, 1, and there was a second vector 2, 1, 2. Now 2 and 2 belongs to the span of the first, right? 2 and 2 just belongs as one of these points over here. Therefore, 2 is called, so the second vector is said to be linearly dependent on the first vector. It's said to be linearly dependent because it belongs to the span of the first vector. And similarly, any vector that belongs to the span of some other set of vectors is linearly dependent on them. So for example, if as I said earlier, there were a couple of where is this? For example, the vectors 1, comma 0 and let's say 1, comma 1 span the 2D space. So that means that any vector, for example, 5, comma 10 is linearly dependent on these two, okay, on these two vectors. And what is the notion of linear independence? When when a vector is not linearly dependent on some of the other vectors. For example, let's go back to that case where we had two vectors, right, in 3 dimensions, which is 3, 2, 1 and 4, 0, 3. Let's say 3, 2, 1 and 4, 0, 3. Okay, so these two vectors basically span plane in 3 dimensions, right? It need not plane in 3 dimensions, and I can always pick a vector which is not on that plane. So that vector, by just intuition, you can see that since it doesn't belong to the plane, it's not in the span of those vectors. And therefore, this vector would be linearly independent of the first two vectors, linearly independent of these two. Okay. So actually, when people say they also, you might see in books that when people say a vector v is linearly independent of, I'm just using li to as a shorthand for linear independence. V is linearly independent of u and let's say w if there is no set of numbers, maybe 10 times v plus 5 times u plus 3 times w is equal to 0. So there is no such choice of numbers that you can put here such that they sum to the 0 vector. Okay, so that's all it means. This is a formal definition, but intuitively it just means that the vector is not in the span of the given set of vectors. Okay. Now, given this notion of span, we can actually Okay, before that, I'll just circle back to another I guess topic in I guess machine learning or just linear regression, which is the notion of multicollinearity. So in this, what happens is, let's say you have a bunch of features and a bunch of features, for example, coming back to that example of predicting income given demographics, maybe, the first feature was age that you wanted to use. And maybe the second feature was education level. Maybe there's some now numeric score for education level, and maybe a few other things. What if there was another feature, down the line, maybe the 100th feature, which was also 10 times age? Somehow you just happen to include that. Then age and 10 times age, if you look at your um, data. So if you think of this as the names of the columns, and then there'll be a bunch of data like 20 years old, and here it'll be 200 for one entry here in the data set, and maybe somebody's 30 years old, and maybe here it's 300. So here you can see that this column, if you think of this as a collection of vectors, right? Each one is a collection of vectors. Each one is a vector. So you can see that the last column is just a multiple of the first one. So therefore, it's not linearly independent of the remaining guys. In particular, it's just a multiple of the first column. So these types of features actually can cause issues. I will not go into the details of what issues it causes. Causes issues, and the technical term they use there is called multicollinearity. Okay. Coming back to this notion of span, um, so span lets us redefine, or actually define a little bit more carefully what is meant by a basis. Okay, a basis is nothing but a set of, a set, or a set of linearly independent vectors that span the space. Okay, so for example, in 2D, an example basis could be 1 0 and 0 1. Of course, another example could be 2 3 and 5 5 10. Let's say some as long as they are not, as long as the second vector is not in the span of the first one, right? So these are, which means that these two vectors are linearly independent, and they span the space, which is a two-dimensional space, and therefore this is a basis and this is also a basis. Okay. In particular, the first one is called the standard basis, and I'll use the shorthand notation E1 and E2 to represent them. So you can imagine, we can generalize that to, if you have 100 dimensions, then E100 would be a vector which will be all zeros except the last entry being 1, for example, right? So the question is, okay, why do we need the notion of span? At least makes sense because of multicollinearity, but why do we need the notion of basis for machine learning? Is because bases are useful to understand, understand data properties through what is called principal component analysis, for example, as well as it can be useful. Basis can also be used to understand algorithms, how algorithms work, how do you train models, basically. So to train models, you will devise what are called algorithms, right? For example, I'll just throw a name. It's called, let's say, gradient descent. And if you want to understand some properties of gradient descent, maybe the notion of basis is useful because you'll be dealing with essentially certain types of vectors there. Okay. In fact, this word gradient should ring a bell, and we'll actually look at it again if you in a refresher on calculus. Okay. So let's move forward. So what have we seen in this video? We've seen the notion of linear combination. We've looked at the notion of span. We understood what is meant by linearly independent and linearly dependent. And then we also define basis as a set of linearly independent vectors that span the ambient space or span the space, right? And there are some nice connections to, for example, classification, multicollinearity, and so on. That kind of these concepts have a bearing on them. Okay, so that's all for this video. Thank you for watching.